Welcome to the second lesson on prime numbers. In the first lesson, I went over a number of theorems concerning prime numbers, and I'll use some of those in this lesson to solve certain problems. And then there'll be another lesson after this on prime numbers, and again, I'll use some of the theorems that I proved in part one in that part also. For our first problem, we have this statement here. If n divides b and m divides b, and the GCD of n and m is equal to 1, then the product m times n divides b. So we need this condition here that the two numbers are relatively prime. And I give an example of if you don't have this condition where things don't work. So 8 divides 16, 4 divides 16, but 4 times 8 equals 32, and that doesn't divide 16. So if you want to give it a try, pause the video here, and I'll come back on the next slide and give the solution. The solution uses the fundamental theorem of arithmetic, which I mentioned in the previous lesson, and I proved a simpler case of this. It states that every integer greater than 1 has a unique prime factorization. So we do that for both n and m. You see here for n, it's written as a product of primes, each raised to a power. So p1 to pk are primes. And then m, we do the same thing. So q1, q2 up to q sub j are primes, and then these f's are the powers that you're raising the prime numbers to. Since the GCD of m and n is equal to 1, the list of primes for n, p1s to p2, p up to pk, and the list of primes for m, the q's, are disjoint. If any of them were shared, then of course the GCD would be greater than 1. Since n divides b, b must contain all the prime powers shown here. And since m divides b, b must also contain all the prime powers of m. Since these sets of primes are distinct, b must contain the product of both sets of prime powers to satisfy both conditions simultaneously. In other words, the conditions of n and m dividing b. So b would be of this form here, some integer L times the product of these two prime factorizations of n and m. In other words, b equals L times m times n, which implies that b divides m times n. Okay, so that was the proof, and again, it all depended on the two numbers being relatively prime, and as well as this fundamental theorem of arithmetic. If a is congruent to x mod n, and a is congruent to x mod m, and n and m are relatively prime, in other words, their GCD equals 1, show that a is congruent to x mod m times n. Let's look at a solution to our problem. First, we notice that the two conditions we were given are equivalent to n dividing a minus x and m dividing a minus x. We can reduce this to the first problem that we did in this lesson. We let b equal a minus x, then we have that n divides b and m divides b, and we're given that n and m are relatively prime. So that all reverts back to the result we proved before. If n divides b and m divides b and their GCD is 1, then m times n divides b, and then we just plug a minus x back in for b, and we have this here. M times m divides a minus x, but that's the same as A being congruent to X mod M times N. I have one more somewhat easy problem, and then I'll get into more involved problems after that. So we have A congruent to B mod C, and the question is it always true that A squared is congruent to B squared mod C? I'll give you the solution on this slide, so if you want to try it, pause the video now, otherwise I'll come back in a second and give you the solution. Okay, so here's a solution. Our condition, our given, A congruent to B mod C, is the same as C dividing A minus B, which we can write as A minus B equals some integer times C. And then we look at A squared minus B squared. We can factor that, A minus B times A plus B. Then we substitute in KC for A minus B. And so we have C times the integer K times A plus B equals A squared minus B squared. In other words, C divides A squared minus B squared, which means that A squared minus B squared is congruent to 0 mod C, which is the same as saying A squared is congruent to B squared mod C. Let P be a prime greater than 3. Prove that P squared is congruent to 1 mod 24. Let's look at the solution, or actually one of two solutions. I have another solution on the next slide. In this solution, we factor 24 as 3 times 8, and we note that 3 and 8 have a GCD of 1. So we can use one of our previous theorems on this. If we can show that P squared is congruent to 1 mod 3, and P squared is congruent to 1 mod 8, then P squared is congruent to the product of 3 times 8, or 24, which is what we want to show. So we'll work on this one first. Since P is prime greater than 3, P is not divisible by 3. Therefore, P must be congruent either 1 or 2 mod 3. So we look at the first case. We have this, and as we proved just in the last problem, we can square both sides here. We get P squared equals 1 squared is congruent to 1 mod 3. Then if P is congruent to 2 mod 3, we can square both sides, and we get 4 here, and that's just the same as 1 mod 3. So either way, P squared is congruent to 1 mod 3. So that proves this case. Now we need to look at this case. Since P is a prime greater than 3, it's P minus 1 is even, right? All the primes except for 2 are odd. So 1 minus, that would be even. That means P is congruent to 1 mod 2, which implies P can be written in the form 2K plus 1. So what we want to do is look at P minus 1 congruent mod 8, and we know that we don't know what X is, but we know there's 4 possibilities. It's either 0, 2, 4, or 6, since we know P minus 1 is even, it's 2K, it's of the form 2K. So we'll look at each one of these cases and see what we can figure out about P squared. Put in X equals 0, we bring the 1 over, and we get P is congruent to 1 mod 8, so P squared is congruent to 1 mod 8, that's good. Then we'll put in 2 for X, again, in each case we're going to bring the 1 over, so we get P is congruent to 3 mod 8, we square that on both sides, we get 9, but 9 is congruent to 1 mod 8, then we use X equals 4, bring the 1 over, we get P is congruent to 5 mod 8, 25, squaring both sides, 25 is, 24 plus 1, so it's congruent to 1 mod 8. Finally, we put in 6 for X, bring the 1 over, we get P is congruent to 7 mod 8. We square both sides, P squared is congruent to 49, but 6 times 8 is 48, so that you get this is congruent to just 1. So in all 4 cases, we get p squared is congruent to 1 mod 8. So we've shown this, and then we have the implication of the result we wanted to prove. Here's another way of proving it. I suspect you might like this better. It's simpler. It doesn't have all these cases. Since p is a prime and it's greater than 3, so it's not 2. It's an odd number, and all odd numbers can be written of the form 2k plus 1. So p squared, we square the 2k plus 1, and then we can, it's actually 4k squared plus 4k plus 1, but we can write it like this. And since k and k plus 1 are consecutive integers, one of them must be even, so we can write k times k plus 1 as 2m for some integer m, and then we get p squared equals 4 times 2m plus 1, which is 8m plus 1, and that implies that p squared is congruent to 1 mod 8. So that's pretty simple. I didn't see that initially. I kind of beat it over the head on the first solution, but clearly this is a better way to do it. Prove that 3 divides n, a natural number, if and only if 3 divides the sum of the digits in n. So I know this isn't a prime number theorem, even though 3 is a prime. It doesn't involve, the solution doesn't involve prime numbers, but I need this result for a problem I'm going to do in the lesson following this. So I put it in here. It's kind of an interesting problem. You may have seen this before. There's a whole bunch of these different formulas for determining whether or not 7 or 10 or 5 or even some numbers in the teens divide a given number by looking at the digits of the number. So this is one of the simpler ones, but I'll go through the details on the next slide as to why this is true. So take our integer n, or natural number n, I should say, in base 10, and these would be its digits. So in other words, if you had 321, then 1 would be D0, 2 would be D1, and 3 would be D2. So I'm just stating this general here. Each one of these digits is between 0 and 9. So we can write n in this form here. This is the unit, this is the power of 10, and so forth. And then we can write it as in terms of this more succinct formula, summation. So let S be the sum of the digits. So it will be the sum of these D0 to D sub k. And then we want to examine the powers of 10 mod 3. Since 10 is 3 times 3 plus 1, we have the 10 is congruent to 1 mod 3. Using the property that congruences are preserved under exponentiation, in other words, if a is congruent to b, then a to the k is congruent to b to the k. We proved this for k equals 2 earlier, but it's true for any integer, any positive integer. So it follows that for any non-negative integer I, we have that 10 to the I is congruent to 1 to the I from this equation here, which is congruent to 1 mod 3. So if we apply that modulo 3 to our equation up here, so we have n equals the summation, then this is congruent to this mod 3, but as we just said, 10 to the I is congruent to 1 to the I mod 3, that's just 1. So this is congruent to d sub I mod 3. So you're just taking the sum over the d sub i's. In other words, this thing here, and that's mod 3. So This congruence, n congruent to s mod 3, implies that n and s have the same remainder when divided by 3. Therefore, if the n is congruent to 0 mod 3, if and only if, s is congruent to 0 mod 3. In other words, 3 divides n if and only if 3 divides the sum of the digits. Okay, so that's kind of clever. It's been known for a long time, but it's an interesting result. So I have another one of these for a different divisibility. I'll show you that on the next slide. We have a similar problem to the previous one. Prove that a natural number n is divisible by 11 if and only if the difference between the sum of the digits in the odd positions and the sum of the digits in the even positions is divisible by 11. So in mathematical terms, if n has the following digits, d sub k down to d sub 0, then 11 divides n if and only if d0 minus d sub 1 plus d sub 2 minus d sub 3 and so on is congruent to 0 mod 11. Okay, so have a look at this and I'll give you the proof on the next slide. So we first note in terms of the solution that 10 is congruent to minus 1 mod 11. You can see that if you just add 1 to the other side, you get 11 is congruent to 0 mod 11, which is true. If we raise both sides to the power I, then we have 10 to the I is congruent to minus 1 to the power I mod 11. And so if n is even, 10 to the I is congruent to 1 mod 11, and if n is odd, 10 to the I is congruent to minus 1 mod 11. And then next we consider the expansion of n in terms of its digits. So as we did with the previous problem, we can write n this way here. And then we can write this mod 11, just plugging this into here. We have that. And so n is congruent to d sub 0 minus d sub 1 plus d sub 2 minus d sub 3. Basically, when you have the odd indices, you're getting a negative because of this here. And when you have the even indices, you're getting 1. So it works out like this. Thus, n is divisible by 11 if and only if the alternating sum of its digits is divisible by 11. Okay, so there are many other divisibility rules for integers, not just 3 and 11. It's things for 7 and 8 and 13 and 17. There's a whole bunch of them. Some of them get quite complicated and they have multiple cases. There's a nice summary of this problem in the Wikipedia article entitled Divisibility Rule, and here's the link to that article. Okay, so for the last problem, I've used this property that if you had two numbers congruent to each other mod a particular number, then you could raise both sides to a power and you still have congruence. So I didn't prove that yet, but I'm going to do that on the final problem for this lesson. So we have a problem here that we've used a few times in this lesson, but I haven't proved it. So I'm going to do that here. If we have A congruent to B mod C, prove that A to the K is congruent to B to the K mod C for any positive integer K. So we did prove it for K equals 2, but this is for any positive integer K. So have a look at that and see if you can prove it, and I'll give you my solution on the next slide. We want to show that A to the K is congruent to B to the K mod C, given that A is congruent to B mod C. And that's equivalent to showing that C divides A to the K minus B to the K. So using the algebraic identity for the difference of powers, we have this here. You can verify this just by multiplying it out. You multiply A times this, and then minus B times this, and most of the terms drop out except for A to the K and minus B to the K. So you have this here. And we were given that A is congruent to B mod C. In other words, A minus B is a multiple of C. So we can write A minus B equals M times C, where M is some integer. We plug that in here. And now we have A to the K minus B to the K equals C times, we don't really care what this is in here other than it's an integer. And so that implies that C divides A to the K minus B to the K, which is what we were trying to show. So that's pretty much it for this lesson. And I have one more lesson on prime numbers, and I'll put that out as soon as I get a chance to record that. And then I'm thinking about doing some additional number theory lessons. I may want to do something on Diophantine equations, but I'm not sure yet. I haven't prepared that yet at this point. Okay, so if you like this, please give it a like on YouTube and stay tuned.